Okay, so just continuing with, or starting section 6.4, this is on simplifying different types of roots or radical signs. This is a cube root. And in general, what we want to do here is split this up and just deal with one component at a time. So deal with the numbers, and then with the x's, and then with the y's. So starting with the numbers first, we want to see if one of these numbers can be pulled out of 54, because those numbers that I just wrote are the perfect cubes. And if you look at it, 27 can come out of 54. 54 happens to be 27 times 2. So the cube root of 27 times the cube root of 2. Let me just move this over just a little bit and give ourselves some more space. So cube root of 27 times cube root of 2. Then I look at x and I say, well, I'm taking the cube roots. I want to see if there's some multiple of 3 that I can pull out of there, because that would make me able to easily take the cube root. And I can break x to the 4th into x to the 3rd times x to the 1st. You could also break it into x squared times x squared, but the reason we're doing x cubed times x to the 1st is because that is going to allow us to easily take the cube root. Same thing right here. How would I break up y to the 5th? Well, since I'm taking the cube root, I want to pull out a y to the 3rd. And then what's left behind to get y to the 5th would be y squared. And now all we need to do is just go down the line and take any cube roots that we can take. So this is 3. The 2 I can't do anything with, so I'll leave it. The cube root of x cubed is just x to the 1st. And when it says use absolute value signs, we use absolute values when we go from basically from an odd numbered power to, we use absolute values like on something like 16, we have an even numbered root that we have to take. So in this case we won't have to, because we're taking a cube root that's an odd numbered power and raising a negative number to a odd numbered power is still going to be negative. So we don't need to worry about that in this problem. Okay, and then this right here we can't simplify anymore, so it's still the cube root of x. The cube root of y cubed is just y to the 1st, or y. And then again, I can't simplify that anymore. So what would our final answer be? We would just take all the stuff outside the roots and combine them. So that's 3xy. And we take all the stuff inside the cube roots and combine them. So 3xy times the cube root of 2x and y squared, because that's all the stuff inside the cube root. Let's double check to see if we have that, and that is exactly what we have. Okay, the next one right here is, let me just bracket this off right here. The next one is a 4th root, and this time we might have to use absolute values, and here's why. Let's do a simple example with square roots. Generally speaking, when we take the square root of something like 25, we only want to get the positive square root. If we wanted the negative, we would put a negative in front. So that generally means only the positive square root, but the problem is I could get either 5 or negative 5. So to avoid that problem, we put absolute values around it. Okay, and here's the rule for absolute values. If you are raising something to an even numbered power, like 5 to the 2nd, second is an even number, and you wind up with something to an odd power, in order to avoid having this conflict between the positive and the negative, we put an absolute value around it, and that will guarantee that it's positive. That only happens when we're going even to even. If we were doing this instead, if we were doing 5 to the 4th, the square root of 5 to the 4th is 5 to the 2nd, and that's guaranteed to be positive, because raising something to the 2nd will always be positive. So we don't need to put absolute values. The only time we do is when we're going from even numbered power to an odd numbered power, and that's for things like this. Okay, so for example, in the cube root one, it wouldn't be possible to go from even to even, from even to odd, or from odd to even. It only happens with square roots or with 4th roots or something like that. So then let's split this up like we did the other one. The 4th root of 162 times the 4th root of n cubed times the 4th root of n squared. And this is kind of easier because we're not going to be able to take the 4th roots of either of these, because this only goes to the 3rd power to the 2nd power. So the only one we're going to be able to do here something with is that first one. So 1 to the 4th. I'm just listing out the perfect 4th roots here so we can see where that takes us. And if you look at, that's 256, 4 to the 4th. If you look at these 4th roots right here, these 4th powers, 81 is the only thing that goes into 162 evenly. So that happens to be 81, so fourth root of 81 times the fourth root of 2. And then we can just combine these other two, because like we said, we're not going to be able to do anything to simplify them. So the square root of 81 is 3. And then we will simplify this or finish this by just combining everything that's still under the root together. So we get 2m cubed n squared underneath that fourth root. And let's verify that that is correct. And it is. Alright, this one is section 6.5. So with these, what we want to do is basically we want to, I'm just going to rewrite this here, we want to eliminate any roots in the denominator. That is what we're not allowed to have. So the first thing is let's write everything as, let's kind of factor it out in its exponents or its powers. So that's supposed to be a fourth right there. So what I mean by that is 27 is the same as 3 to the third power. Okay, that way we can see what we're working with in terms of exponents. And then we want to do something called rationalizing the denominator. And the way that that is done is we basically ask ourselves, what do I need to be in the denominator to get rid of that fourth root? Okay, well I need this to be, if I'm taking the fourth root, I need that to be the fourth power. I have 3 3's there. How many more do I need to get to the fourth power? I need 1 more. I need 3 to the first. How many more k's do I need to get a fourth power, or something close to a fourth power? I need 1 more also. And then I have to multiply the top by that same thing, because, you know, if you're multiplying by something divided by itself, you're going to get 1. So that blue fraction right there actually equals 1. And you're allowed to divide, or to multiply and divide by 1, because those end up being the same thing. It doesn't change your answer in the So what's 3 to the third times 3 to the first? That's 3 to the fourth. What's k to the third times k to the first? That's k to the fourth. What's 4 times 3? That would be 12. And what's k to the fourth times k to the first? That's k to the fifth. And actually, well, we'll leave it as k to the fifth for now. We're going to have to simplify it in just a sec. So the bottom, the fourth root of 3 to the fourth is just 3. That cancels. And the fourth root of k to the fourth is just k. That also cancels. And that was the goal. We don't want any roots in the bottom. The top is still going to be the fourth root of 12, but then let's split off k to the fifth into k to the fourth times k to the first. Why would we do that? Because that will allow us to simplify this. The fourth root of k to the fourth is just k, so that is now outside the fourth root, and then underneath it is still the 12 and the k to the first. So we'll combine those into 1, so we get k times the fourth root of k to the fourth root of 12k, and the only last thing we can simplify is this k cancels with that, and we're left with the fourth root of 12k over 3. That is a simplified version. So let's check that we get the fourth root of 12k over 3 as our answer right here, and we do. Alright, one more similar problem right here. So let's just kind of bracket this off right here so we don't get in the way. So this is going to be 2xy over the cube root of, and then I'm going to factor the 9. So 9 is 3 to the second. And then we have x to the fourth y squared. And then again, I want to ask myself, well, how can I get rid of all the stuff in the fraction? I need to have things showing up. Since I'm taking the cube root, I need things to be cubed, or some power of cube down here. So what is that going to wind up being? Well, I have 2 3's right here, and I would like to have 3 3's. So I need another 3 to get 3 to the cubed. I have x to the fourth, and I would like to get something that I can easily divide by 3. I can take the cube root of, and that would be x to the sixth. So if I have 4 x's, that means I need 2 more to get to x to the sixth. I have 2 y's, so I would need 1 more to get y to the third. And then we need that same thing on the top so that it's balanced, so that we're multiplying by 1, or the equivalent of 1. Alright, so now let's simplify this. We're going to have the cube root of 3 to the second times 3 to the first is 3 to the third. X to the fourth times x to the second is x to the sixth. Y to the second times y to the first is y to the third. What does the top become? Well, actually, we can't do anything more in the top, because the top didn't have anything under a root, so we're just going to have 3x squared y. That thing is just going to join to the 2xy. Alright, now let's simplify a little bit more. So the cube root of this whole thing, that's going to cancel these cubes. We're going to get 3, or we're going to get y. And what's the cube root of x to the sixth? But really what you're doing is raising something, taking the cube root is like raising it to the 1/3 power. So you're basically dividing that 6 by 3, or taking a third of 6, which is x to the second. So that's what the bottom is. The top is still 2xy times the cube root of 3x squared y. Is there anything we can simplify here? There is. We can cancel out these y's right here. We can cancel one of those that x right there and one of the two x's down here. So our final answer would be, yes, it would be 2 times the cube root of 3x squared y over 3x. And that should be the answer. Let's double check that we get, what is it, 2 times the cube root over 3x. So we get 2 times the cube root over 3x. That does work. Alright, last two for this video is how do we multiply roots together like this. So the easiest thing to do is kind of what we were doing before, is to start off by factoring any numbers. So negative 16, by the way, this is the same as the fifth root of negative 1 times 16p to the fifth. So the fifth root of negative 1 is just negative, so I'm going to pull that out front right at the beginning. 16 is 2 to the fourth power. P to the fifth is still there. And then 128 is 2 to the seventh power. Okay, 2 to the 7th, so we're looking for powers of 2, and then we have p to the fourth right here. We knew we were looking for powers of 2 because that was 2 to the fourth. So let's simplify this. We have negative, and let's combine the 2's. The fifth root of 2 to the fourth times the fifth root of 2 to the 7th, and we'll combine the variables together. The fifth root of p to the fifth times the fifth root of p to the fourth. Still have that negative in front. This is going to be the fifth root of 2 to the 4 plus 7 is 11. And now that's the fifth root of 5 plus 4 for the exponents, and p would be p to the 9th. Okay, now, last thing we want to do is just separate this in such a way that we can pull out powers of 5. So the closest power of 5 to 11, sorry, the closest multiple of 5, I should say, is 10. So 2 to the 11th is the same as 2 to the 10th times 2 to the 1st. And how about for the p's? Well, p to the 9th, we kind of could have done it up here at this point. P to the 9th is the same as p to the 5th times p to the 4th. And now let's simplify this. So negative, well, we're supposed to divide these exponents. The fifth root of 2 to the 10th power is like 2 to the second. It's just 10 divided by 5. Okay, the fifth root of p to the 5th is just p. So both of those are now outside the root. And what is left behind, what's left behind is just 2 times p to the 4th. We can combine those. And here's the final answer. Negative 2 squared is 4. So negative 4p times the fifth root of 2p to the 4th. That is as simplified as we can make it. So let's double check. Negative 4p times the fifth root of 2p to the 4th. There it is. Alright, last one. Very similar problem here on number 20. So let's begin again by, because we're taking the cube root of a negative, we can just pull the negative out front. And then what is 12 factor to? 12 is the same as 4 times 3. And 4 is 2 to the second. And 3 is just 3 to the first. And then we have the n right there. And then let's factor the 9 as well. 9 is 3 to the second. And then we still have that n squared. So we'll put all the things that are like each other together. We have cube root of 2 squared. Well, there's no other power of 2 under there, so we're not going to be able to do anything with that, so we're just going to leave it alone. Okay, then we have the cube root of 3 to the first times 3 to the second. This thing times this thing, that's going to be 3 to the third. Okay, and then the next thing we have is the cube root of n to the first times n to the second. Well, that's going to be n to the third. So now we can simplify a little bit more. And let's see what we have. So we have negative, this thing, the cube root of 3 to the third is just 3. The cube root of n cubed is just n. And then I can't do anything with 2 squared, so I'll just leave it as 2 squared. Or let's just change it into what 2 squared is, which is 4. So we get that answer, negative 3n times the cube root of 4. And there is our result. So in the next video, we will work on now adding and subtracting radicals or roots together, which is the remaining part of 6.5.